Okay, hi everybody. Welcome to the refresher lecture. And good morning, good afternoon, or good evening, depending on when you're watching this video. In this lecture, what we're going to do is we're going to go over the main themes of the psychometrics course again. And we'll be sure to pay a little extra attention to the theory behind those exercises and those topics that you indicated were a little bit difficult during the refresher tutor groups. This lecture is going to be cut up into 5 different videos. A video on reliability, a video on validity, a video on dimensionality or factor analysis, a video on bias, and finally a video on real-life decision making. Because that way it will be easier for you guys to scroll back and find a topic that you want to listen to again. We might include some additional videos depending on questions that come out of the refresher tutor groups, but the idea is to have these 5 videos. So reliability, validity, dimensionality, bias, and real-life decision making. And this one, video 1, is going to be about reliability. Now, before we get to reliability, I wanted to mention classical test theory again, because basically the entire 2.5, 3.5 course was based on classical test theory. And this theory states that an individual's observed score is made up out of 2 separate parts, the true score and some measurement error. So in mathematical formulas, the observed score xo is equal to the true score x underscore subscript t plus x subscript e. Now, what we want to measure is the true score. So when we're testing somebody, we want to know their true mathematical ability, their true level of intelligence, their true level of depression. But the thing is, we're never able to measure those actual levels perfectly in social sciences. There's always some measurement error going on. So we want xt, but what we always end up with is xo. And then hopefully xo is going to be mostly true score and only a small part of measurement error. But classical test theory states that observed scores are part true score, the thing we're after, part measurement error, the thing we don't want, but we just happen to get every time. Okay, now, one of the main assumptions of classical test theory, and one of the most important ones, is the assumption that the true score of an individual does not change. So we're assuming that if we give the same test to the same individual, let's say 50 times, then on each of those test occasions, the person's true score will be the same. Now we can have an entire discussion about whether that assumption makes sense. I think that most of the time it probably doesn't, but that's the assumption of classical test theory. Now that doesn't mean that the observed score will be the same every time. As you can see over here, first time the person got a 10, second time he or she got a 12, third time 7, and the cave time 9. So the observed score will vary from measurement occasion to measurement occasion, but the true score will stay the same. So the differences in observed scores are purely due to measurement error. Okay, now, as I mentioned, this video was going to be about reliability. And reliability basically asks the question, if I give the same test 50 times, 100 times, a million times, if I give the same test over and over and over again to one individual, how similar are the observed scores I get? So ideally what you want is, if you give the same test over and over and over again, you want to get the same test score over and over and over again. Now, as we already mentioned, that's not going to happen due to measurement error, but that's what we want. And reliability is the degree to which we're measuring the same thing each time. Okay. Now, the reason reliability is defined like this, so the reason that reliability looks at, if I take the same test over and over and over again, do I get the same score over and over and over again, has to do with classical test theory. As I mentioned, classical test theory assumes that the observed score is part true score, the thing we want, part measurement error. Now, since classical test theory assumes that the true score doesn't change over time, reliability should give an indication of how well our test is measuring the true score. Why? Well, like I said, the true score should stay the same. So if my test is measuring the same thing over and over and over and over again, then that should indicate that my test is really giving a good measure of the true score. Because the measurement error, that's random. That should fluctuate from measurement occasion to measurement occasion. So if there's little fluctuation between test scores, then there should be little measurement error in the test score. So reliability should give a nice indication about how well our test is measuring the true score. Now, one important thing about classical test theory and this assumption, it's nice that classical test theory states that an observed score is part true score, part error score, but the thing is, classical test theory doesn't really check whether it's true score or error score. It can't determine whether part of an observed test score is true score. We don't know the true score, we can never see the true score in social sciences, so we can never be sure what part is true, what part is error. What we can do, and what we do in practice, is we check what part of an observed test score is systematic and what part is unsystematic. So we check to what degree does a test score stay constant over time, which will be the systematic part, and to what degree does a test score fluctuate over time. And the fluctuations will be the unsystematic part. So we want to divide an observed score into true score and error score. We can't do that. What we can do is divide it into a systematic part and an unsystematic part. And what classical test theory does, and what isn't necessarily correct, is classical test theory states the systematic part is all true score, the unsystematic part is all error score. Alright, we're gonna get back to that a little bit later. Okay, so classical test theory, it states that an observed score is part true score, part error score. Can't really do that, can only check systematic, unsystematic, but classical test theory assumes systematic is true, unsystematic is error. And reliability checks to what degree observed scores of the administrations of the same test over and over and over again are the same. So the higher the reliability, the more repeated test scores are the same, which according to classical test theory is a good thing, because the more it stays the same, the more the test should be measuring the true score. Alright, now, as an example to make this all a little bit clearer, hopefully, we use this ice skating example in the lectures. What we were looking at the 2013 Olympics in Sochi, and we were looking at the 500 meters skating event. And the observed score was just the time in milliseconds that the skater took to finish the 500 meters. Okay. Now, what influences this observed time? Now, obviously, skating ability, skating skill is an important part. And skating skill, you could say, would be the true score here. So the true number of seconds that somebody needs to finish 500 meters based on skating skill. Now, the skating skill, according to classical test theory, should stay the same from occasion to occasion. So it's systematic, which is fine. So if you have the same skater with the same level of ability, if he does the 500 meters over and over and over again, if everything is perfect and the skating skill doesn't change, he or she should have the same score, the same time every time. Okay. Now, are there any other circumstances that could influence his or her time on the 500 meters, but that don't change from one measurement occasion to the next? And the answer is yes. Unfortunately, there are. And this is the part that classical test theory does not take into account properly. There are other systematic influences that don't change from measurement occasion to measurement occasion, so that have the exact same effect on measurement 1, measurement 2, measurement 3, and so on. And in this example, you could think about quality of the ice, for example. If the ice is really, really bad, then times will be slower, but times will be slower each time they're skating on this specific ice rink. So quality of the ice here is a systematic part that in classical test theory gets sucked up into the true score, into xt, but obviously has nothing to do with the actual true score, the actual ability of the person to be measured. Alright, so we have the observed scores, XO, milliseconds of the time they take to finish 500 meters. We have the systematic part, which is part actual ability, part what we're actually trying to measure, part actual true score, the skating skill, but also includes some other systematic influences, like for example quality of the ice, and as I mentioned here, you can also think about temperature and air pressure. Now, what accidental influences could we have on a person's time? Well, you could just have bad luck. You could just slip by accident. You could have a bad cold, which basically influences your performance here, but if you would come back like a week later, everything would be fine. It also depends on whether the final turn you take on the 500 meters, do you have the inside lane or the outside lane, which might make a little bit of difference. All those influences will affect your time, but if you do the 500 meters a second time, the influence will be different. So if you have the inside lane now, and next time you have the outside lane, so that influence cancels out. If you have a bad cold now, next time you'll feel better, so that won't have an effect again. So the insystematic part are influences that don't influence the test score each and every time. They just influence the test set one time by accident. And one final time, classical test theory assumes that the observed score is part true score, part error score, but the only thing we can determine and the only thing we can check is what part is systematic, what part is unsystematic or accidental. Classical test theory assumes that all systematic influences are true score, but that's not necessarily a good assumption. Okay, now before we get to reliability, let's list some assumptions about classical test theory that will influence how we look at reliability. The first assumption of classical test theory, like I mentioned on the slide, we already mentioned observed score is part true score, part error score. That was one assumption. And the other assumption was that the true score is unchanged over time. Those were already two assumptions of classical test theory. Another assumption of classical test theory is that the average measurement error over n repeated assessments is equal to 0. This is basically a complicated and mathematical way of saying that good luck and bad luck cancel out. So if you happen to be lucky and score a little bit too high on one measurement occasion, you probably be unlucky and score a little bit too low on the next measurement occasion. Sometimes you have good luck, sometimes you have bad luck, but in the long run you end up neutral. So the average measurement error over repeated test administrations is 0. Another assumption is that the residual, so the measurement error, since they're just purely accidental events, right? Measurement error just happens by accident, and because it happens by accident, it's not related to anything. So measurement error is not related to true scores, it's not related to the true score in Y, it's not related to the true score in X. If you have two different tests, then the measurement error in the first test is not related to the measurement error in the second test. The only thing, and this is a little bit, well, it's a little bit lame to basically make this statement, but the only thing that measurement error is related to is its own observed score, but that's a little bit, I don't know, it's a little bit lame, like I said, because as we said, according to classical test theory, the observed score is made up out of true score and error. So obviously, the higher the error, the higher the observed score. The lower the error, the lower the observed score. It's the sum, and it's part of the sum. So it's related to the observed score, but that's more or less by accident. But based on theory, because it happens by accident, error is not related to anything else. Alright, now that we have all those assumptions out of the way, now that we refreshed classical test theory a little bit, let's look at reliability. Like I said, reliability just comes down to to what degree is my test measuring the same thing over and over and over again. And since we're looking at classical test theory, and since the thing that should stay constant from one measurement occasion to the other, so the one thing that should stay constant over and over and over again, according to the classical test theory, is the true score. So reliability is conceived as a way of getting to the true score. What part of our test score is actual true score, but the only thing that we're measuring is what part of our test score remains constant across time. So we're checking what is systematic, but according to classical test theory, that's the same as saying looking at what is true score. But remember, as I mentioned, systematic variance is not all necessarily true score variance. It's not all a measure of a person's ability. There are also other systematic influences in there. Alright. Now, let's look at this Venn diagram. So the entire circle represents the total variance in X. So the entire circle is the total observed score variance, S squared XO. Now we know, based on classical test theory, part of that circle is the variance of the true score, XT, which is actually systematic variance, and part error variance or unsystematic variance, S squared XE. Now, if reliability measures or looks at what part stays constant over time, basically reliability is asking what part of that entire circle is purple. So what part of the total variance is systematic variance, what part of the total variance is true score variance. And then we can just get reliability by taking the purple part, dividing the purple part by the total circle, and determining what percentage or what proportion of the total circle is systematic variance. So basically we're asking what part of the total circle is this purple part. How much of the circle is purple? And if you want to write it down in fancy mathematical symbols, it basically comes down to asking what percentage or what proportion is the true score relative to the observed, or the true score variance relative to the observed variance. So we can do true score variance or systematic variance divided by the total variance. This gives us a measure of reliability. Alright. Now, I'm going to give you 3 more measures of reliability, but basically they all come down to the same thing. They all check what part of a test remains constant over time. And basically they all ask and answer the question, what part of the total variance is systematic variance? They just answer that question in different ways. But this is the most straightforward way. Check what part is systematic variance, divide the systematic variance by the total variance, that's your reliability. Now, second thing we can do, since we're interested in what part of the total circle is purple, we can also ask what part of the total circle is not purple and subtract that proportion from 1. So basically we're doing the exact opposite of method 1. Method 1 really checks what part of the total circle is purple. Now we're going to ask what part of the total circle is not purple and subtract that from 1 to get basically the exact same information. So the total variance is 100%, hence the 1. And from that 100%, we're going to subtract that proportion, that percentage of the circle, which is error variance, and basically doing 1 minus the, what is it, grayish part, so 1 minus the error part, just makes us end up with the purple part again. So like I said, we're basically going to do the same thing over and over and over again. So reliability is also a measure of lack of error variance. Alright, now these 2 methods both are formulated basically in terms of explained variance. Now explained variance, we're not used to seeing that a lot. We've seen it when we were talking about regression. When you're doing a regression analysis, you check R squared, you check explained variance. But apart from there, we haven't talked about explained variance often in statistics courses. Now, what we have talked about a lot, and which is a statistic that we can easily get, are correlations. And as you might remember from those regression lectures, explained variance, r squared, is basically just a correlation squared. So I can rephrase all of these measures. So I can do method number 1, method number 2, which is basically in terms of explained variances, so basically in terms of r squared. I can rephrase these in terms of correlation, because explained variance is just correlation squared. So, how can I also check what part of this total circle is purple? Well, I could check the correlation between the true score and the test score, so the total observed test score, test the correlation between XO and XT, and if I then square that correlation, I get the reliability. Because if I square the correlation between XT and XO, what I end up with is the explained variance, so that part of the variance in XO that's explained by the true, by XT. So by squaring the correlation, I get that part of the circle that's purple, which is basically what I wrote down here. And finally, I can do method number 2 in the correlation type phrasing. I can say, okay, I'm going to check the correlation between XE and XO, take the square of that correlation, then I get the explained variance in XO due to XE. So basically, by squaring that correlation, I figure out what part of the circle is error variance, and then if I do 1 minus the percentage, I end up with the reliability. Alright, now, this was the theory, but now how do we do it in practice? Now, in practice, it's nearly impossible, well, it's basically impossible, to do method 1 and method 2, right? I mean, we don't know what part of the score is true score, we don't know what part of the score is error score, so we have no easy way to divide observed variance into a true score variance and error variance. I mean, if we could do that, we would be rich. We wouldn't need psychometric courses, we could just get to the true score straight away. So there's no easy way to have one individual test score and divide that into true scores and error scores. We can't do that. What we do know, however, is that this true score part, and remember true score is just systematic and error is just unsystematic. What we do know is that this systematic part should stay the same from one measurement occasion to the next. So if I take the same test over and over and over and over again, I can't divide individual tests into systematic parts and unsystematic parts, but if I have multiple measurement occasions, I can figure out what part remains constant and what part changed. And the way to do that is by looking at correlations. The higher the correlation between two different measurement occasions, the more those two measurement occasions are the same, right? So correlations then are a measure of how stable, how constant measurement scores or test scores are over multiple administrations. So correlations can give us an insight into what part of repeated assessments are stable, are systematic. Alright, so getting at the systematic variance and unsystematic variance, and so getting at reliability, the key to do that apparently is correlation. Great. But then correlation between what? Well, and that what has multiple different alternatives. So we can look at correlations between different things. And what thing we put in there basically determines what measure of reliability we use. The first thing we can look at correlation between is two alternate forms of the same test. So we're going to give two tests. The two tests are not exactly the same, but they have the same type of questions and the same subject. So think about the actual course exam for psychrometrics and RECIT. Those two exams are not exactly the same, but the questions have the same format, they're about the same topics, and they're also more or less equally difficult. So those are alternate forms. Now, since those alternate forms should be more or less similar, we can see those two forms as two administrations of the same test. and we can look at the correlation between those two alternate forms to figure out what part of those test scores is systematic. Alright, so alternate forms, we give two parallel forms to participants. Half the participants get form 1, the other half get form 2, for example, and we can look at the correlations between those two forms, and that correlation gives us the alternate form's reliability. Now there is an issue with this, and the issue is that it's really hard in practice to get perfectly parallel tests. Two alternate forms are rarely exactly identical difficulty-wise, etc., etc. So we can't guarantee that the true score of the two alternate forms are the same. There could be differences there, and we can't guarantee that the error variances are the same, because it's really difficult to get two tests with items that measure the underlying construct with the same degree of reliability, the same degree of precision. So we're assuming that they're exactly the same. We can't test that. They probably aren't exactly the same, and that will influence our measure of reliability. What people often do is check whether at least the observed average scores on the two forms are the same, and whether at least the two observed variances on the two forms are the same. But these don't prove, they're a good check, but they don't prove that the true scores and error variance are exactly the same. So the idea behind alternate forms reliability makes sense. You have two tests that should be equal in every sense. So by looking at the correlation between the two, we should get an idea about what part of the variance is systematic variance, but in practice getting to exactly parallel forms is difficult, and that basically is a problem for this form of reliability measurement. Now, you might say, if it's so important that the tests are exactly the same, why don't you just give the same test twice? Well, good point. People thought of that. I'm going to get back to this later. And when they did that, they called it test, retest, reliability. So if you do that, you just give the same test twice. This should solve all the problems of alternate forms reliability, right? So this should solve the problem that forms might not be exactly parallel. True? True, it's the same test, so they are definitely exactly the same. But the problem here is that you shouldn't forget that what we're measuring in social sciences are people. And people have this thing called memory. So if you give the same test twice, the problem is that the second time they probably remember one or more of the answers they gave the first time. So they don't respond to the second test administration the same way they did to the first. So in that response, in that respect, even though it's the same test can't be considered exactly equal to the first one, because people remembered what they did. They saw the test before, and that changes people's experience of the test, so to say. Now, nice thing then, as I said, advantage compared to alternate forms is that its content is definitely the same. Disadvantage is content is the same. So the benefit here is also the downside. Alright, so these are the two ways to test reliability with two different test administrations. Either the same test twice or different, hopefully similar versions of the same test. Now, the key then is looking at the correlation between these two different tests, either the two alternate forms or the test and the retest, and that correlation should give us a measure of reliability. However, and I'm just gonna go on and on about this one part, so here it is again. However, remember that what correlation is measuring is what part of the variance of those two tests is constant, is systematic. So we're looking at what part or what variance that was present in the first measurement occasion also is present in the second measurement occasion. What I'm saying is, remember that we're dividing observed variance into systematic variance and unsystematic variance. We're not dividing into true variance and error variance. We can't see true, we can't see error, we can only see systematic and unsystematic, And classical test theory assumes that the systematic part is the true part. Okay, now, problem with this, the systematic unsystematic thing is that if there are differences that happen from one point to the next, even if that difference occurs in the truth course, so let's say I'm measuring psychrometrics ability and I'm measuring it with the course exam and I measure it with the resit, if people learned more psychrometrics, so their psychrometric ability changed from test to the resit, the fact that the true score changed means that the systematic variance in those two tests is different. And the weird thing is that increase in true score, when looking at correlations, will be assigned to the error variance part. Because it's not similar between the two tests, even though it is true score, even though it is something systematic, the fact that it's not similar in the two tests means it gets assigned to error variance. So everything that changes gets assigned to error variance, even if that's not necessarily what you would want. Alright, so that means, there we go, that means that there are two possible issues that might influence or might bias your reliability estimate. Like I said, one part is true scores can change. Psychometric attributes like intelligence, depression, stuff like that are rarely stable. People's true score fluctuate over time, and those fluctuations lower your reliability. A change in true score is not assigned to the true score part as it should be. It's assigned to the error part because it's different from one measurement occasion to the next. And things that are not exactly equal get assigned to the error part. The second thing that can happen is that the error part changes from one measurement occasion to the next. Oh, sorry, that one error part influences both measurement occasions. Sorry. Now, even though it's error, even though it's something accidental, so let's say we have two alternate forms of a test. You have test version 1 and test version 2. During the course exam, we give you guys test version 1 and test version 2. Half makes version 1, the other half makes version 2. But let's say that during that exam, the lights go out. So there's difficulty with electricity, the lights are blinking, there's not really nice lighting. Does that lighting influence your true scores, your true knowledge about psychrometrics? No, of course not. Will that influence your test scores, however? Yes, obviously, because it's really, really annoying. So is it something systematic? No, it has nothing to do with your true scores. Is it something accidental? Yes, if we give you the test next week, we would assume that electricity is fine, so it's just this one measurement occasion that is negatively affected by those blinking lights. However, since both alternate forms are administered at the same time, that accidental measurement error part influences both form 1 and form 2. So the influence is present in both your tests. Since it's present in both tests, it gets assigned to the systematic variance part, even though it isn't. So correlations help us distinguish systematic from unsystematic variance, but keep in mind that correlations can be fault. If the systematic part changes, correlation will think it's error. If the error part influences both tests, correlation will think that it's systematic. Alright, this applies to the alternate forms. Reliability, we can do something similar obviously for the test retest. Thing with test retest, however, is that as for the measurement error influencing both test administrations, as I showed earlier, that's less likely to happen with test retest. Alternate forms are usually administered at the same time. The test and the retest obviously are not administered at the same time. So the same accidental event happening on the retest and on the test, chances of that aren't that high. So that carryover thing probably won't happen with the test retest part. This true score changing thing, however, so the first way to fool your correlation I mentioned, that's even likelier to happen with test retest reliability than with alternate forms reliability. Like I said, true scores change. If the systematic part changes, correlation will think that's error variance. For alternate forms, that probably won't be such a big deal because both forms are administered at the same time and your true scores don't change from second to second most of the time. But if you look at the test and the retest, and there's a couple of days in between, as I said, most psychological constructs are unstable. So during the retest, your true scores are probably a little bit different than during the test. So this changing true score part is more of a problem for the test retest. This error variance influencing, or this error variance getting mistaken for systematic variance, that's more likely for the alternate forms test. Alright, moving on. So these were the two reliability measures that you can calculate if you have two tests, so either two forms of a test or the same test twice. But the downside of that is that obviously you have to have two versions of a test or two administrations of a test. That's a lot of hassle in practice. So people started asking the question, can't we just calculate reliability from one test administration? The answer was yes, you can. Then you can just say, okay, I'm going to look at parts of my one test, and I'm going to consider those parts parallel administrations of the same test. So I'm not going to make an entire parallel form of a test. I'm just going to take one test and say, you know what, the second half is basically the first half. So I can see the second half as a parallel form of the first half. You could do that. Now, same difficulty as with parallel forms reliability applies to this internal consistency reliability. It's really hard to have two test halves that are exactly parallel. So it's nice that we can do it with one test administration, but doing it with one test administration doesn't solve the parallel forms difficulties. It's still difficult to get parallel parts of tests. Second difficulty with this internal consistency measure is the longer the test is, the higher the reliability. So the more items you have, the more accurately you can measure. So obviously if I just cut a test in half, I lose some of the information which influences my reliability. Fortunately, the second part, we can correct for that with the formula for internal consistency reliability. Now, one issue with this is, sure, it's fine, we can cut the test in half, we can check the correlation between those two halves to get an idea about reliability, but the way that I cut the test influences my reliability. So if I just take first half, second half, I will get a certain correlation. If I take even numbers versus uneven numbers, I will get a correlation that's slightly different. So the way that I split my test influences my measure of reliability. Now obviously that's a little bit awkward and something that I try to avoid. So what we can also do to get around that is use Cronbach's alpha. Cronbach's alpha is also an internal consistency measure, but it takes basically cutting your test into pieces to the extreme. Cronbach's alpha sees each individual item as a parallel replication. So it says item 2 is basically parallel to item 1. Item 3, yeah, that's basically parallel to item 1 and 2 again. So it sees each individual item as a test administration and all items as a set of administrations that are parallel to each other. And you could prove, which you don't have to, that if you do all possible split halves, all possible ways of cutting up a test and calculating your internal consistency reliability, if you then take the average of all those reliabilities, you would basically get Cronbach's alpha. Now here's the formula, I won't go into that. And the nice thing about Cronbach's alpha is the most widely used measure of reliability. Why? Well, one, it's easy, you only need one test, you don't need parallel forms, you don't need test retest. 2, it's always the same, so it doesn't depend on the way that you split your test. 3, it's in SPSS, so it's also easy to get. And 4, it's slightly less strict than the other measures of reliability. For Cronbach's alpha, it's not necessarily the case that both the true scores remain the same and the error variances remain the same. Only the first part is a real assumption. The second part, this equal error variances, is not an assumption of Cronbach's alpha. So it's also slightly more lenient than the other reliability measures. Now, that doesn't mean that Cronbach's alpha is perfect. I mean, this equal true score part, this assumption, is difficult all by itself. I mean, the true score part of each item probably isn't exactly the same. So that's what I wrote down here. The true scores of the individual items are probably not all exactly the same, and because of that, you often read that Combas alpha is a lower bound estimate of reliability. It gives a slightly underestimated reliability estimate. Now, this is true. This equal true score part almost never holds, and because of that, you would get an underestimated reliability. However, remember that we are using samples, and we are using one test administration. That means if there's a measurement error part, something accidental happening, like what I was talking about, the flickering lights, the electricity problem, that measurement error will affect all items of the test. Because it's affecting all items, it appears to be something systematic. Combas alpha will also think that it's systematic because it's influencing all items. Because of that, measurement error with Combas alpha can lead to overestimation of reliability. So if there's no measurement error at all, yes, Combas alpha is a lower bound estimate, but since measurement error is always a possibility, you could well have an overestimated reliability. So in the population with no measurement error, yes, Combas alpha underestimates. In practice with samples, no, Combas alpha is not always an underestimate. Your sample Combas alpha can either underestimate your reliability or it can overestimate reliability, because there's always measurement error. And remember, apart from measurement error, when you have a sample, you also have sampling error. So it could be that your first sample just happens to be a sample with really low Combas alpha. Your second sample could be slightly above average. Your third sample could be really above average Combas alpha wise. So the population Combas alpha, yes, it always underestimates reliability. The sample Combas alpha, not necessarily. It can underestimate, as you can see, but it can also overestimate due to measurement error or due to drawing a sample that's really extreme, which gives you a really high sample Combas alpha, and a sample Combas alpha that's really far away from the actual population value. So due to sampling error and due to measurement error, the individual sample Combas alpha can either underestimate or overestimate reliability. Alright, that's it for video 1 on reliability. The next video is going to be on validity.